This is understanding and hardening the attack surface at the edge. My name is Tim Madison. I'm the Global Tech Lead for IoT Partners. My job is to help partners understand how to use the IoT services, how to incorporate those services into their products, and connect partners to other partners to build even more systems on top of AWS. And we'll be joined later by one of our partners, Zymbit, to demonstrate their hardware security module. So what we're going to talk about today is first the attack surface, what's out there, what you can be attacked by. And then I'm going to give you what I think is the one piece of advice that you should use to harden your system if you can choose only one thing to do. So let's talk about the attack surface. And first of all, why it's important. The NSA says attacks always get better. They never get worse. Allegedly, they say this. I don't know that they actually say this, but everyone loves to quote them and say that this is something that they've said before, and it's true. The best example is, denial of service attack or some type of buffer overflow may just crash your application, but eventually somebody's going to turn it into an exploit where they can run code on your system. And I've heard from customers and partners before, they say, well, the data that we've got isn't really all that important, so we don't really feel like we have to protect it that much. Now, the thing that you have to realize is no matter how important you think your data is, you never know who's going to use it downstream, even if you think you do. So if it's simple as temperature data, it's got to be secured because somebody's going to take that temperature data and they're going to want to use it to turn on and off building automation systems or something. So any piece of data that you've got, if it's not important enough to protect, don't bother collecting it. So what we'll do is we'll start from the physical interfaces and we'll move out step by step from the different components at the edge to show what can be attacked and how. So the number one thing that you can be attacked on physical devices when you've got possession of them. Something near and dear to me, I worked on a project that was a Linux embedded device, and it had a console port. And at the time, we said, oh, it's not really a big deal, until we realized that what the console port provides is a root shell that you cannot put a password on to the Linux environment. So we very quickly had to turn that off. But there's a lot of systems that have console ports, whether they're Linux or embedded devices, that people don't realize how much access they provide. And it's so easy, if it's RS-232 or some other simple serial protocol, it's so easy to get into that port that you have to physically turn it off or physically destroy those connections so that somebody can't make use of them. Another thing to look out for is serial ports. I mentioned RS-232 for the console port, but sometimes you have things like Modbus and BACnet and LANWorks and all these legacy protocols. A lot of the drivers for these things haven't really been tested for security purposes. They're always sitting on some type of private physical network that everyone feels like they don't need to worry about. So they haven't been fuzzed, and they probably can crash very easily. And again, attacks always get better. They never get worse. So if somebody can inject bad data into your system, potentially they'll crash this driver and then get root access to your system eventually. And then there's flash. It's very easy if you don't take steps to protect your flash for somebody to just take your device off the shelf, pull the flash off, and just read it. And there are ways that you can protect it, and we'll talk about that in the next slide. But if somebody can get to your flash and read the private keys off, it's just game over. As soon as somebody's exfiltrated the private key, there's really nothing that you can do to protect yourself because you may not even know that they have the private key. And at any time in the future, they can go ahead and use it and attack you. So often customers say, well, we're going to use Secure Flash and Secure Boot. And Secure Flash and Secure Boot, I'll be very clear, you should be using both of these things, but they don't solve all of your problems. So let's talk about what Secure Flash actually is. Secure Flash encrypts the flash so that when the device is reading and writing from the flash, when your microcontroller is reading and writing from the flash, the blocks that go back and forth are encrypted. They end up on the flash encrypted, they get decrypted in RAM. That's great, and if somebody tries to pull your flash off and it's encrypted and they don't have the key, they can't do anything with the data. But it doesn't protect you from an application that's already on the system or a piece of code that's been injected into the system. Because when that piece of code goes to ask for a block from the flash, oftentimes the operating system, whether it's a real-time operating system or Linux-based operating system, is going to get those blocks right from the OS decrypted for it. Because they assume if the code's running on the device, it should have access to those blocks. So the encrypted file system is transparent to the applications that are running there. So Secure Flash protects you very specifically from somebody pulling the flash off and reading it. But that's about it. And Secure Boot is great because it lets you make sure that you have your software when you boot up from a trusted source. But it still doesn't protect you from other things like injecting code into your system, bugs in your system, compromised development systems, all things that we're going to talk about in the next few slides. It's great that the code came from you and not from somebody else. It means that if somebody pulls the flash off, they can't necessarily just inject any code that they want for the device to boot up and use. But it still doesn't mean that they can't get code into the system in other ways or find other bugs to compromise. So secure flash will protect you from your flash being pulled. Secure boot will protect you from code at boot time not being your code, but that's about as far as they go. So if we take a step back from the device itself, most of the time these devices can be plugged into a network, or maybe they're on some kind of Wi-Fi network, and they're going to have an over-the-air update system. Now, later we'll talk about Linux and the over-the-air update system of a package manager. Maybe you don't control the package manager, so you have no idea where those packages come from. But a lot of OTA systems on systems on embedded devices, they're homebrewed. People aren't using some kind of standard system that's been out for years and years and years. They figure, oh, I just need to patch a few blocks in the flash, so I'll just make it myself. And these systems are not hardened, and oftentimes they can be man-in-the-middle impersonated. There's all kinds of ways that these things can be attacked. I've worked on systems where they thought the security was good enough, but if you had the source code, if you can get the source code, you could figure out how to compromise it pretty easily. Insecure services, there's some free, embedded operating systems that will have services running on it that you don't necessarily need, maybe a time service or something like that. Again, it could be an older component that hasn't been hardened, so there's always the risk that somebody is going to be able to send some packets to it. Again, crash it and inject code into your system. And then there's remote denial of service. If somebody gets access to your network, even if they can't get access to the device, even if they can't compromise the over-the-air update system, even if they can't break into your system through some kind of insecure service, maybe they can provide a remote denial of service. And for a lot of devices, this is as simple as sending like a very large ping packet and just having the device just chew through that packet in memory. So it's only a denial of service, but if it's a critical system, like that's a serious vulnerability. You can't just have it go down because somebody pinged it. The next step out from that is the development infrastructure, and this is something that gets missed a lot because people just imagine that it's, they have developers committing code and everything is nice and secure. So, the code repository, you've got SSH keys, developers are committing code to it with their SSH keys, and it's great. It's backed by Git, and you have hashes on all your commits, and you know all the code that's in there. But you don't necessarily know who's committing the code. Maybe you have an employee that left, that kept their key. Maybe you don't have good processes around reissuing those keys. You have to be very sure you know at all times who is committing code to these repositories, because eventually that's going to get built into your artifact, it's going to get sent downstream. So if somebody can find a way even to compromise your developer's system and inject some code there, and the developer commits it themselves, it still gets into your repository, still ends up compromising your system. And then continuous integration systems. So you might have something like Jenkins running, pulling your code, and then building it, and you might not think like, oh, I need to secure Jenkins, but even if all of your code is secure, if Jenkins pulls some code down and then you can get in there and modify the file system, it's just the same as putting commits. It's probably even worse than putting commits in, because then nobody can see it. It's just a transparent, vulnerability that just shows up in the field. Like, this is not the code that we thought was running, but we have no idea where it came from. And in a similar vein, the staging areas for build artifacts. Oftentimes you'll have a continuous integration system, builds a build artifact, which is your non-signed firmware or something. If somebody can compromise that staging area, if you've got maybe some public bucket that you didn't really think to lock down properly, somebody can go in there and read the file and then patch a few bytes in it. Downstream, if you then sign it, it doesn't matter that you've got secure boot, you've just signed the code that somebody patched that is not your code. So then let's talk about real-world social engineering attacks. Hopefully everyone's got cool barbed wire like this, so nobody can possibly attack you. But realistically, there's so many ways that you can be attacked, and the attack surface here is really, really large, because first it could be the deployment processes. Somebody could social engineer somebody whose job it is to take that final artifact and actually deploy it to the devices in the field. And even if that code is signed, one of the vulnerabilities is maybe somebody can use an old artifact that they know has vulnerabilities in it, downgrade your devices in the field, and then you've got a big problem. So if that person can be social engineered, or if that process of deployment is not secure, then you've got some trouble you need to deal with. Installation processes. There are plenty of devices that come out of the box with no keys, and some installer has to run some application, generate a key, and then copy it onto the device. Now, whatever that device is, iPad, phone, whatever, if somebody can get the installer to give them access to that device and get access to these private keys before they're being downloaded into the device, problem as well. So you need to make sure that when you're getting keys onto the device or when you're generating keys, that you have a secure process to do it. And we'll talk about that. So for embedded devices at the edge, a lot of them have reduced capabilities, and sometimes it's a good thing because there's only so much you can do to them. There's typically fewer things to attack, but if you don't have sufficient security mechanisms for the device to protect itself, you don't have a memory protection unit, you're not securing your keys properly, you don't have secure flash, you don't have secure boot, you're running old code, you don't have all these processes in place to protect yourself. There's only so much you can do, and you really need the top-notch hardware, which is very inexpensive now, to protect yourself against these things. And expanding on that, Linux has all of these same kind of challenges that we talked about for the embedded devices, and some of them were mixed in with Linux vulnerabilities as well. But there are other things that people miss as well. Like Linux devices, when they're deployed in the field, oftentimes they're maintained or managed by SSH. But sometimes it's a hassle to distribute keys to people, so they use username and password authentication. Or the hassle to distribute keys turns into everyone uses shared keys. And people miss the fact that it's pretty easy with SSH to do two-factor authentication, with a YubiKey or something like that. They just never turn it on. So if you have the opportunity and you're using SSH to maintain your Linux devices, make sure you're not using shared keys, make sure you're using two-factor authentication, when it's possible. To prevent all of these kinds of things with keys leaking and somebody potentially breaking into your system via SSH, because once they've done that, they can do a lot of damage. Again, software updates. This is similar to what I was talking about before with OTA, but specifically with software repositories. If you have a device that's running Ubuntu, you don't control the Ubuntu package repositories, probably. I don't think anybody in this room directly controls those. So when you're doing software updates, one thing you want to be really careful about is don't just do apt update and just get the latest version. If you've tested your system against some particular artifacts, make sure you're checking the hashes of those artifacts, make sure you're using exact versions of things. Don't blindly do software updates like that. If you're running Linux at the edge, you almost certainly, if you haven't locked this down, you almost certainly have extra services running. And if you have legacy devices, some of those extra services are definitely vulnerable. Who knows how old the device is, but maybe it's running, again, simple service like Time, NTP, but it's a super, super old version, or maybe it's accidentally got some incredibly old version of SendMail still installed, like something really horrible like that. You need to really look and see what extra services are running, because it's so easy to miss them out of the box. You didn't install it, but it comes with the distro by default. You're running on a Linux device, you're running so much code that you didn't write. The kernel is hundreds of thousands of lines. The latest release of the kernel added, I think, 350,000 lines of code. And yes, they removed some, but it's hundreds and hundreds of thousands of lines of code just in the kernel alone. That is not code that you've written and not code that you've audited. And just because it's open source doesn't mean that some open source angels have gone through it and made sure that it's totally safe. That's just not the case. We know that that's not realistic. There's plenty of open source projects that people find zero-day exploits in all the time. It's great that it's open source because people can look, but it doesn't mean that they actually have looked. So it's clear there are lots and lots of things to worry about. And I don't want you to come away from this talk saying, oh my God, I'm never going to deploy a device again because there's no way that I can deal with this. So I'm just going to say we have to start somewhere. And I've done presentations like this many, many, many times, and we've given people tons of different things that they can do. But we always land on this one thing that we believe that they should do first to improve the security of their embedded device. And I'll just reiterate this: there is hope. If you can only improve one aspect of your entire system to protect the attack surface in your edge system, it's super simple, and it's in giant text in a second. Never have your private keys in main memory. When I first started working on embedded projects, I was either naive or the hardware didn't exist. I always thought, if I have a private key and I need to do some type of crypto operations with it, I'm going to load it off the flash, the encrypted flash, I'm going to load it off the flash into main memory, do my operations, zero out the memory as quickly as possible, and that's the best protection I can get. But that's not the case anymore. There's much better protection you can get. And that protection comes in the form of secure elements, TPMs, trusted platform modules, and HSMs, hardware security modules. They allow you to lock away the private key. And similar, if anyone's used STS, the secure token service for IAM, it's essentially similar to that in that you never get the private key out of the device. You always ask the device to do something for you with the private key. and it does that operation on your behalf, and it passes you back the result. You're never getting a copy of the private key that you can put in main memory. And it's standard practice in the embedded space. People have been doing this for years with all different kinds of products, and it's becoming slowly but surely more popular in the Linux world. And specifically on Monday, we released a new feature for Greengrass called Greengrass Hardware Security Integration. And this allows you now to use the hardware secure element, or TPM or HSM, to take your private keys that you use to authenticate to AWS IoT Core and the AWS IoT Greengrass services, use that hardware and lock away your key there. Previously, if you look at the configuration for Greengrass, before we had the HSI feature, very simple. Your configuration here just says, I have a certificate and a private key, and they're on this path in the file system. And what we've done now is now we use PKCS11, and we let people specify what PKCS11 provider they're going to use, and then what slots and pins that they're going to use to get the keys out if that's necessary. And then we tell Greengrass, when you go look for the private key is not there. There's this virtual path for it. So rather than trying to do the crypto operations in main memory, pass them off to this library. Now this example here is libsoft_HSM. It's a software HSM. It's really for testing purposes. So when you're starting to work with Greengrass and you want to see how to use this particular, the HSI feature, you can set up soft HSM and you can see how it works like this. But in the real world, we want to move beyond the theoretical, and we want to see, like, what hardware can we actually use to do this? Soft HSM itself doesn't provide any protection for you. It really is a development tool. So we need to see this thing working. So that's why today we have Zymbit here, Zymkey, and they're going to talk about their HSI integration and their product. But I wanted to share with you an example of a project that we have internally. This cool-looking device here is called the AutoCrib, and it's an industrial vending machine. And inside the AWS data centers, we have these things where somebody goes into this area in the data center where they're going to do a job. They're going to replace a drive or replace memory or something like that. They're not allowed to bring anything with them. You need to go through a serious amount of security to get into this area, and then you get there and you have no tools and no parts and whatever. So you go up to this machine, and you enter your job code, and it says, you're here to replace a drive, you're here to replace a drive in this location, and it vends those things to you out of that. Now this thing has some software by default, but we wanted to customize it. AWS, we spend a lot of time optimizing our processes. So our data center team has an integration with this system that runs on a Raspberry Pi today, and it allows them to tie it into their own job management system. And the data center operations team, they're called the Smash team actually, which I think is a much cooler name. They have this tenet, which is just to increase the security and efficiency of AWS data centers. So what they chose to do was use the Raspberry Pi, because for them it's a viable production product because of the environment that it's in. But they wanted to add some more security to it. They said, right now the keys live on the flash, and as we said, never have your private keys in main memory. They said the same thing to us, so we had a conversation, and found out that they were actually using the Zymkey. They were testing the Zymkey already, and now that we have this HSI feature, they can now use it with Greengrass. So what they're using is they're using the Raspberry Pi with the Zymkey and Greengrass, and they use Greengrass as a deployment mechanism to send code down, and they use the Zymkey to protect their credentials so they can connect to AWS services, and that's where their job management system runs. So that's the story about the AutoCrib, and again, Zymbit's created this production-ready part that Phil Strong is going to talk about in a second here with the Raspberry Pi style header. So without further ado, he'll do a better job of it than me. Let's talk to Phil Strong.
Thanks, Tim. Who knows what a Raspberry Pi is, first of all? Okay, half of it. Who uses a Raspberry Pi in their production environment, or, okay, some at the back. All right, so it's a real product, and what we found, I mean, we think of the class of Raspberry Pi as single board computers. What we do at Zymbit is we make security modules for those single board computers. And we, really the way we think about security is a whole device security. If you're in a data center, you think about the whole data center. Well, we think of edge devices as little data centers. Every one of them has to have its own security that looks after the whole device. So we're going to talk about that in a bit more detail. And basically our job is to make those devices hard to penetrate, but it's also an important part of our job is to make it really easy to integrate these things. I think one of the biggest obstacles to security, particularly in the IoT space where there's so much variability, is it's really hard to do it. So part of our job is to make that easy for you to integrate security into your system. So let's kind of talk about what that looks like in the wild. Typically, this is a typical application. So this is an oil well production instance, and we have some of our equipment protecting this kind of equipment. It lives out, obviously, it's outside a firewall. It has no physical infrastructure. There's no chief security officer. There's no guardians for this. There's no one to go in and put a password inside it. So it's completely naked from a security point of view. Secondly, often these devices, people plug things into them. Someone's plugged in a different sensor or plugged in a different monitor. So there's often a whole bunch of unsanctioned devices in there that you, back in the data center or back in the control center, have no idea what's been plugged into it. And then often you can't rely on the power. So typically the power's up, but you have no idea if someone switches the power off. And same with the network. Networks can go down. So there's a lot of moving pieces here that really you don't have control over. And a centralized security model doesn't have control over that either. So what we need to do is really push that security down to the device itself. So Tim talked earlier about sort of the value of data, and I think his point was that if you're collecting the data, it has value. Couldn't agree more with that. And here's maybe a slightly different way to look at that. From what are the things that are typically stored in an edge device? Often, particularly in the IoT space, the edge device itself, the computer board might cost you $50. Might cost you $500, but let's say it's in that $50 range. The memory side of it is $5, but what's inside that memory? Typically, you're storing credentials for all the services. You've got maybe credentials for a file system that's encrypted, and you have application data in there. Your application data, it might just be temperature data that's worth whatever, a couple of bucks. It might be temperature data that's totally critical to your process and be worth thousands of dollars, or it may be priceless. So the data that's on those devices also has inherent value. The thing we see the most, though, is that people get to the point where they're about to deploy their code, and then they realize, oh, actually my whole company's code is in this thing. I've got a $5 SD card, and I'm putting 10 million bucks worth of code into this SD card. That's, all of a sudden, you have to figure out, how do I deal with that? How do I secure it? So, we like to think of the $10 million SD card, and then we also encourage you to think about, well, what's the consequences if this system is breached here? And consequences can be commercial, like, okay, my data got out, I've lost a whole bunch of customers, my brand's damaged. But very much so in the IoT world, a lot of these things have physical consequences as well. So something's going to blow up, someone's going to get killed, traffic lights are going to be messed up, and so there's going to be a collision. So there are real physical impacts which, from a monetary point of view, can be millions of dollars, and they can have life-threatening impacts too. So it's a big deal. It's not just a $5 card. Right at the top of that is this, the keys to the kingdom, as we call them. Where do you keep the keys? And typically those keys are stored in a secure element of some kind, which might be 50 cents. So with P, it's only 50 cents. But if you think about that 50 cents could actually expose that 50 million bucks. So, yep, keys protect the valuable digital assets you've got in there, but the big question is, and the question no one likes to ask is, yeah, but who's protecting those keys? So that's really what Zymbit is all about, protecting those keys. And I like to show this. Many of you have seen it in terms of the castle. People have been protecting keys for thousands of years. And in the old days, they keep them in the keep. That's what it was called. Yeah, the keys would get put in the keep, and they build a wall around it, and you'd have all these layers. So the concept of a layered approach is not new, and transfer that to the IT space, to today's technology, it's all about defense in depth, which is used. We like to think of it as whole device security, where you put all those together and you can you have whole security around the device. So take that idea and say, well, how on earth would I build that into a piece of technology, into a security module? And that's really what we're doing here. So I'm going to go through these layers, and then we'll get to some physical product, and you can see what the product looks like and where you can buy it. And so our first job is to protect those keys. Yeah, and we start with the secure element. Secure element has a number of functions in it. It generates and stores keys in hardware, in a piece of silicon. It's a specialized piece of silicon. It has a crypto engine in it, typically, which is going to be used to sign and encrypt data. And it'll have some other cryptographic functions, a true random number generator, maybe some SHA capability in there. It's got a bunch of cryptographic functions, and we can certainly get into those specs afterwards if you're interested. On top of all that, this is a specialized bit of silicon that has what's called an active shield. So if someone is really determined, people say, well, what if they shave the silicon? What if they go in and start to pull this chip apart? First of all, it's going to be probably a state nation that does that. That's an expensive proposition. Yes, it's possible. But most secure elements have an active grid on top of them, which protects that to a high degree. So all starts with that secure element. We happen to use one from Microchip, who's been, that's another Amazon partner and AWS partner. So we built our product around that secure element. Secure element is just that. It stores the keys. So when you think about, well, how do I interface this with the real world, what we've done here is add a security supervisor. What that security supervisor does is it basically isolates the secure element from the real world. It provides an encrypted communication with the secure element, and it adds an application layer, which really allows you to deal with application-specific features. So that's a security processor. We call it a supervisory processor. We package all that up into a module, and the module is a physical module about the size of a piece of gum. We have different flavors of that gum, if you like, and different sizes, but the way we look at the IoT space is that most customers come to us and say, oh, I need to add this, and I've got to ship something in 3 weeks or even in a week. So the idea of having something modular that you can physically add is an important aspect of this product. The other important aspect is that the security gets built in at the point of manufacture. In this case, when you add a secure element or when you add a module to the device, you really have to ask yourself, well, who's putting those things together, and do I trust that point of integration? So if you can buy the modules from a vendor and you can buy the computer from another vendor, and you actually put them together yourself in a trusted, within your secure, trusted management system, then you have control over that final provisioning of the device. So making it modular is kind of a key thing, particularly in the IoT space, where you might be deploying 5,000 or 10,000, maybe 100,000 devices. If you're deploying millions of devices that are all the same, then you can have the luxury of putting the chip on the board. But putting a chip on a board is not easy. So that's where we wrap these up in a module here. The other key thing of a module is that when the power goes down or when the network goes down, your security processor needs to continue to be alive, and therefore it has to have its own power. We have a battery backup system, we have a real-time clock on board, so if you lose network connectivity, you still know what time it is. And losing track of time is an attack vector. I don't think we touched on that explicitly, but if you don't know what time it is, you can wind time back and get in and do things. So having a local onboard time is really important. Okay, so I'm going to zip through this one. This is all about another layer of abstraction here, and you can go buy the data sheets for these chips. So if you were sophisticated, you might say, oh, I can talk to these chips in this way. Here's the communication that I need to do. But what we've done is wrap that in basically in an abstract layer, and we've simplified the communications, so it means that you get high-level security functions that don't expose all the intricacies of the secure element to your application. So that abstraction is, again, another important way of, it does two things. One is it makes the thing hard to talk to deliberately, and then second, it makes means you've got this limited command set. My other point on that was just this OEM capability. So sometimes you want to add in an OEM command or an OEM feature into the API. You can do that. You can't do that with a secure element. If you have a secure element, all of the features of that are typically going to be locked down in software. Okay, so now we're getting to the two outer layers, and then we can get into real product. We're all familiar with identity, and it's really important that your individual devices have a unique identity. And there's no one there to put a biometric in place, or no one to type in a password. So typically, the way we do it, and other people do it too, is that you measure the system. So it's called a measured fingerprint. And what you would do there is basically, what we do is we take in multiple factors. We look at the single board computer it's attached to, we look at the chips, we look at the SD card and take all that information and say, okay, this is the unique system, and we're going to assign it to this unique identity. And what that does then is it means that it's really hard for someone in the field to change out an SD card or change out a computer for some nefarious computer from an unknown source. It means all those pieces are bound together. And if you know, from a point of manufacture, if you know the source of all those pieces, once you bind them together and have a unique signature, then that's locked in for the lifetime of that product. Again, the last part of this, which is very obvious, but actually not that easy to do when you're in a production environment, is the physical aspect of security. How do you deal with a physical attack? Literally, someone pulling the thing off the wall or hitting it with a hammer or prying it open. So there are some very basic techniques we use, but they're integrated right into that framework. First is perimeter circuits, and think of that basically as a couple of barbed wire fences that are digitally, they're digital fences, if you like, and if someone breaks through one of those, then that's going to create a security event. So we have two perimeter circuits. We monitor the power on these devices. As I said earlier, we have independent power, so it's important to monitor the power on the device and know if someone, one attack vector is actually to turn the power on and off very quickly, or to just turn it off completely. So you obviously want your security on all the time. And then the last piece is just physical attack. So we have an accelerometer on most of our modules, and what that does is that we can just see if it's outside of its normal operating zone. If a device is on a wall for 90% of its life, then we're going to know if it's moved. So physical security is an important thing to look for as well. So you put all that together, and basically this concept of whole device security is what we're offering here as a solution. It's physical security, it's digital security, and it's supply chain security or integration. Okay, so the good news is that you don't have to put all that together yourself. What we've done is put all that in a physical module, and all of the things that we talked about, physical tamper detection, device authentication, real-time clock, they're all in this device. And this is about a $40 device in one-off pieces. What that does, this is an example of what we call Zymbit4. It's a model that is designed specifically for the Raspberry Pi. The application that Tim talked about earlier that's used in the AWS data center uses a Raspberry Pi and uses one of these security modules. So it's plug-in, as I talked about, it can be put in right at the end of your development cycle. It connects to the GPIO headers, and it has a couple of APIs available. That's doing three things. The first thing is that perimeter detect, that dashed line around the outside, and checks the perimeter. Second thing it does is it authenticates the hardware in the system. And if the perimeter detect and the authentication check out, then it's going to open up that secure element and release the keys or release the services. The keys are never released, but they're made available as a service. So what we've done then is taken that and integrated that with the AWS IoT Greengrass and HSI integration. And that whole chain now is available, sort of plug and go within the AWS framework. A couple of other applications canned, ready to go. A lot of people ask how to encrypt their file systems and how to integrate it with AWS and also the secure element. We have examples that are ready to go with that using LuxKey and deEncrypt. All of documentation from this product is available online. So good community support. We have a developer kit here that will be available as a standard product as well. At this point, it's more of a developer kit. And what this does is it supports the Zymbit4, which is for Raspberry Pi. We have a feature product, Zymbit6, which is more OEM-oriented. Comes with all the Tamper switches built in. It locks the cables into the package. So you can think of this as a brick with the cables locked in there. And it's often something people forget about is that they build a secure box and then you can plug the cables in and out. Well, it's really important that you actually have those locked in as well. And this is particularly for an industrial environment where 24 volts is common in commercial building applications or industrial. So that will be available next year, January next year. We talked a lot about Raspberry Pi, but this product is also certainly compatible with everything that has a Pi GPIO header, many flavors of Pi. Even the ASUS Tinker boards have compatible header connectors on. And then there's some other flavors of Linux single board computers like BeagleBone and Odroid. And we have certainly built products and solutions around those, and we have standard solutions available in Q1 next year on those. All of these products are designed in the US, so we build them in an ITAR compliant facility, which obviously is important from a security point of view. We have all that chain of custody and audit around the manufacturing process. Also means we can build hundreds of thousands or millions of these devices here in the US. And the other important part is that the design authority for this, we have total control over that. So we often get OEMs who start with a standard product and will want to change it, or they'll want to integrate it onto their board. We can do that here. And so we have that capability in-house. Typically from a dev cycle for us with a customer might be 2 to 3 months. From I've tried the standard product, I like it, can I get something custom? Okay, product. So this is real product. It's available through Premier Farnell and the Newark network, and that's a global distributor. You can buy it in the US, you can buy it in Europe, you can buy it in Asia. And right now they have the Zymbit4 specifically for the Raspberry Pi. There will be other products coming online too through them. So that's basically the end of my piece. What we're doing is security modules specifically for edge devices that make the things hard to penetrate, just like your data centers. But most importantly, they're really easy to integrate because often that's the barrier to actually doing it. You have to make this stuff and make it happen. So we make it easy. Okay, thank you. I think we have some Q&A if people have questions. Tim?
Part.
Fun part. So is anyone doing like device security, edge security? Does anyone actually have that problem set today? Okay. So we're going to pick on you for the first question. Have you got a solution? Does it work? Or?
Yeah, it's a little bit more of a smaller embedded device, so it's an edge device, but with a pretty low-end ARM processor on it. So we had to pretty much engineer everything individually. So encrypted file system, all those sorts of things, but not many percent, but with using the secure boot mechanism to store everything encrypted on the device.
Okay. So you had a question, this gentleman here.
Yeah, the certificate has to be renewed or revoked. How again it has to be brought back to the service center, or how does it do that?
Jim, do you want to answer that?
If the certificate needs to be renewed or revoked, I mean, generally when you have the stance that I take is if you have your private key locked away in a device like this, there's usually no real reason to rotate the certificate. If nobody can get at the private key, there's no real benefit of rotating the certificate. If it needs to be revoked because it's because the device is like stolen or compromised or something like that, yeah, you can definitely do that. You can do that in the service, at least the AWS IoT service. You can revoke it. There's no problem there. But yeah, I wouldn't necessarily recommend rotating the certificates. I mean, you can do it in the case where if you've issued a certificate, but the lifespan of that certificate is really short, usually we tell people to set it, if they have good security on the private keys, set that expiration date as long as you possibly can, but sometimes they get set too short, so if you need to rotate it, you can. We do have some patterns that we recommend to people to rotate certificates, and it can be done through the service. We provide APIs to do that, but you would need to go through the process of rotating the certificate, which leaves your private key the same, but essentially sending a certificate signing request saying that you need a new public sign certificate, getting that down to the device, validating that you have it in your possession, and then invalidating the old certificate. Or if it's already expired, it doesn't really matter. But generally, we recommend reconnect with the new certificate, and then make sure that you invalidate the old one, and then just continue on. But yeah, keep the life of the certificate as long as it could possibly be if you've got your private key locked up like this.
So you talked about the system being able to be aware of whether there's tampering or potentially a security event. What kind of actions do you have available to be taken in that instance where that perimeter circuit is cut, or accelerometer is going crazy? So what kind of options are? Is it pre-built in terms of response, or is it?
It's configurable.
Configurable.
Yeah.
For the benefit of everybody else, the question is, when there's a security event, what kinds of actions can be taken, and is it configurable?
Yeah.
Sorry, go ahead.
And so what we can do is you can configure for nothing, in case you've got a floating. There's two tamper detect inputs. So if you have one that's floating, you obviously don't want to be detecting nothing. So you can do nothing. You can do notification only, or you can do burn the keys. So this will actually kind of mission impossible the whole thing and say, everything's gone. Yeah.
So in which case, yeah, it's just completely smoked then. And sometimes that's the right solution. Sometimes it's not. But
Right.
You spoke about what you said, passwords. There could be some default passwords shipped by vendors themselves, and also some services could be just like that. Maybe keep it on for some no reason. Sometimes that happens. So, is there a policy template which could be available as a part of infrastructure? I don't see anything like that.
So just to repeat that back, so there are a lot of things that can go wrong in the device. There can be a lot of default passwords set. There can be a lot of processes running there that you don't want. Are there options with Device Defender to detect and audit those things? So
Compliance check.
yeah.
Say, for example, policy compliance is one of the requirements
Sure.
which we control most of the devices.
Yeah, so Device Defender, if people are not familiar with it, Device Defender is a service that we provide that allows you to send metrics up to us, and then we can analyze them and see if there's some kind of errant behavior that you should act on. And there are two ways to use it. You can use it on your own. You can send those metrics up on your own, or you can use the Device Defender agent. Now, in today's version of the Device Defender agent, it sends back data about how much data is going across the wire, how many TCP connections are open, what ports are open, and things like that. There isn't support immediately now for enumerating those services, but I know that the team is always looking for feedback like that on what would be there. So I could imagine in the future, if you want, we can get you hooked up to talk to them and submit a feature request and tell them about that. But yeah, it would make sense for that agent to be expanded in the future to provide those kinds of compliance checks, especially on something that's like Linux class, where there are many, many things that can go wrong. I mean, something as simple as being able to send back the list of running processes, or send back the list of things that are in init that would be run at boot up, would be something that would be useful to send back to the service that you could audit it across your fleet. So yeah, if you want afterwards, I could take down your information. We can get you in touch with them.
Sure. It could be something like a list or a CIS, the policy compliance,
Mm-hmm.
which is available for other platforms. But this is an embedded system, obviously. We cannot use that.
Right.
There should be something else probably that probably is coming.
Yeah. The Device Defender service is relatively new. It was launched in April, I believe. So yeah, I think that's a direction it could go.
With the unique device, I guess, brain's failing.
The fingerprint?
Fingerprinting, that's the word.
Yep.
What's the difficulty in transfer, if the core device underneath breaks, or the Raspberry Pi breaks, and you just want to attach this to a new system, what's the difficulty on that, or what's that configuration like? Is that something that you just do through Greengrass, and you'd be able to say, all right, now this is your new buddy, or how's that work?
So again, the question for everyone, with the system that Zymbit has, there's this concept of measured device identity, the fingerprint. If you need to then move the Zymbit device to another system, are there mechanisms to do that? Is that a good summary? Okay.
So,
Oh,
go ahead, Phil.
So the current answer is that we make it difficult for that to happen, yeah? And so it's a return to factory, and that's kind of what the bulk of our customers have asked for. It's like, okay, if this thing fails in the field, we don't want people to service it in the field. They'll do an exchange program. The box gets shipped back, it gets repurposed. So that's the current state of things. But we certainly, get that question more as it goes into commercial applications. And I think there are some ways we can hook that up with the concept of a master key, but as Scott probably can allude to, and that has its own risks too. Okay, who has the master key or master keys? But there's a real requirement, and it depends on the asset you're protecting, of when someone comes out to service it, what level of authority do you want to give them? And right now, it's kind of zero. It's just take the box out, put the new box in. There's no component exchange. I don't know if you want to add to that, Scott.
Oh, sorry.
No, I think that covers it pretty much.
Actually, just kind of piggybacking that question. So, is there a way to control what pieces you use to create that fingerprint? So, here's an example. We've built something on a Raspberry Pi, but just recently we actually had our SD card go back. So, in a case like that, could I create it in such a way that my identity doesn't include the SD card, so I potentially could send a replacement they could use and just swap out?
That's a possible feature request. Right now, we don't have that capability, but certainly we could build something like that in. Yeah, right now the model is, we recommend to our customers use the best quality SD card you can, for various other reasons as well, but this way you're less risk prone. So use the best card you can, and
Now, what you use to create that fingerprint is pretty much standard for you.
right, yeah.
But we have talked about some of the OEM features. So sometimes we'll get asked, okay, well, we have a keyboard, or we have a QR scanner or whatever plugged into our system, and we want that particular scanner to be part of the fingerprint. Can we put that in? As an OEM feature, we can put it in.
So that's the other side of it. If you wanted to add more to it, we could certainly do that.
So now
as
you're
well.
really locking down the sort of surface, if you like, of, well, if you change anything in this box,
It's not
we're
gonna
going to
work.
know.
So that's a great point. So our Pi actually has the Pi camera attached to it too.
Right.
There you go. And if you can pull an ID off of it, we can actually add that into the fingerprint.
Yeah, sorry, and again, I forgot to repeat the question, but the question was, the measured identity measures certain things. Is there an option to turn some of those things off or configure it?
Yeah, it's always that balance between convenience and security. We can make it totally convenient if you want. Any other questions out there? Okay.
I assume you didn't mention this, but the measured identity, that must be generated in production, right? So it's tied back to.
Correct, yeah.
And production means, well, maybe two bits to your question. Do you want to repeat the question?
Yeah, so when is the measured identity created? What step in the process of producing the device is the measured identity created?
So the factors that go into it are part of our, part of the standard product, standard factors. And then the actual physical, once the components are physically married together, let's say it's in your contract manufacturer or maybe you're doing it, once those are married together, it's at that point of integration that the fingerprint gets taken. So it's the first time you boot it up, it basically goes out and scans. We have a concept called production mode and developer mode. Developer mode, if you change the pieces, it's just going to relearn the fingerprint. But the minute you go to production, you then lock it down, and then it's locked permanently. Okay, anyone else thinking up hard questions? No? Great.
Okay, well, we'll be around for a couple more minutes. If you want to catch us in the hallway or something like that, feel free to ask more questions. But again, it's a very late session. I really appreciate everybody attending, sticking through the whole way, so thank you.
Yep, thank you.
Thank you.